So today we're going to do, I was just talking about introduction to data modeling over there. We're down over here doing advanced data modeling. There's no intermediate. You're either beginner or you know everything. So hang on. Let's do this. All right, so advanced, what is advanced? Really, what is advanced? I can say that there are two schools of thought here, right? So you have this, the formal, the professor, isn't it true that your data model is completely mathematically incorrect? Do I look like this guy? No. And then there's more of what I like to do. The practical end of it, I'm a gunslinger. A good one, though. And you know the good ones because they're up here and they're not dead. No, I'm kidding. But I'm much more practical on the practical side. Now, what am I going to do for you today? What would you rather have? Professor or some gun shooting? I'm going to do a little bit of both. And I know that there are plenty of reasons to have both of these. Now, when I say gunslinger, the practical side, I'm not saying doing things wrong. I'm saying that there's a lot of times you can build things and you don't need to go through a formalization for it. And probably, I mean, if any of you lived through the hell that was called the rational process, you know that we didn't do that after a while because it sucked. We've gone through every other methodology. I think I've lived through every software programming way since the beginning of time, since Grace Hopper. And yeah, I used to work for her, by the way. And this is what I wound up doing every time. Agile, it kind of is it's a little less formalized, right? So let's talk about some formal data modeling methods for those of you who are into that. And I want to show you what those are. I will call these right shark. So when you need to level up on your data modeling game, and I have taught this class, and it was pretty irreverent, but you need to start, there's levels that we work through. And this is the formal data modeling process, as defined. So, an open water bottle right freaks me out. I've lived in California long enough to know that nothing is steady. So now we're going to, first step of any formal data modeling is understanding your data. And that's this, very touchy-feely, but it's true. Right? We need to get that conceptual data model, like, all right, what is our data trying to accomplish? Then you need to understand the access patterns, the queries. What are people going to try to exercise from this data? Because this is what our intent is. We want to make this useful data. So that's our query graph, or workflow. And then we're going to try some sort of query-driven data workflow, try to get into this methodology where we can use formalization, say, if you're trying to do X, then you can do Y. That's the logical data model. And finally, we want to take all these optimizations, the formality of it all, and distill it into an actual file that we can install on our computer. That's where we get the CQL. And that's our physical data model. Most times you'll see me down here. I like to build physical data models. I like to build code. So that's where we're at. So let's walk through the steps. So a conceptual data model. This is really, this is where there isn't a lot of utility. This is where you probably are going to work on a big project. You do want to go through some of this. Because it shows, especially if it's a large project, it shows you kind of understand what the domain is. And that is really important. Because I've been in too many projects where, oh, we'll just do something. Oh, that was wrong 6 months later. You find errors. Errors are there. And then the interesting thing is it's technologically independent. We can create data models or conceptual data models that have nothing to do with technology. And ERD, Venn diagrams, those are all, yeah, I know we use those in relational databases, but they are not dependent on relational databases. So they tend to be graphical, they're pictures. People can look at them and say, oh, I get it. You're totally screwed up. So conceptual data model looks something like this, where we have different entities. We show all the different relationships between them, and then we would show the attributes for those entities themselves. Sorry, my graphics are a little janky. I upgraded it from Keynote 9, and my life has been hell. This is a conceptual data model. It says nothing about what database we're using or even what technology we're using. But it shows enough concept here. It's like, oh yeah, okay. Yeah, we're going to have some users, and this is for a digital artifact system. So users, they can post reviews. Yeah, okay, I get this. And you can talk to business owners about this. Product managers. Product managers, they need some help. So you can take that and go into an application query workflow. Now, this is an important part of the Cassandra data model. Those of you who were in my last talk, that you start with this query. Like, what are you going to ask the database? Why are you going to ask the database this thing? Okay. So, Cassandra is an application database. It will be asked questions. Are you going to get the right questions in there? Can you support those with the data model? So here's an example of an application query workflow. This is mapping out what our application will do. So we'll do a search by artifacts, and then we'll display a rating for a particular artifact, maybe, or display information for a venue. These are like steps that you can think of like clicking on buttons on your website. These are going to generate different kind of queries in your database. This is not a bad place to be. You should at least be talking about this before you start data modeling with Cassandra. Now, what you get out of this is you get this. You get questions. Those questions are these access patterns, these queries. It's like, okay, find artifacts for a specified venue. That's Q1. Okay. To get to Q1, I have to search for it first. Then I can go to Q5, Q6, Q7, Q8. And these are where all my queries are down here. I'm asking questions in my database. I'm creating queries. Now, that application query workflow will lead into what's called the logical data model. This is what you eventually will see is probably more familiar, because what you're going to get out of this is mapping. It's like, here's the data tables that I have to create. This is how they're going to work. These are what we call Chapko diagrams. There's actually, I know this guy. His name is Artem Chapko, and he's one building a lot of this formalization for data modeling with Cassandra. He's a professor at the university. Well, he was, and I worked for data science. But he's developing the courses for a formal data modeling class, and which makes a lot of people happy. So you get this, the logical data model. It shows the queries I can operate against tables, awesome, and those queries, what they should look like. So we can look at this before we write any CQL and say, does this make sense? Are we missing anything? I think we got this. And from there, we create our physical data model. And that physical data model is a bunch of CQL queries. And you can see we put some types to these. We've showed order, our clustering columns, our primary key. It's all there. That could be easily translated into a CQL file. So that, in a nutshell, very quick nutshell, is the process that we do formal data modeling. Now, I'm going to switch gears and move more into practical. Practical data modeling is where I probably spend most of my time. If I've ever been on site, and we're a customer data stacks, and I've ever been on site, this is probably spend most of our time. We talk about your application, we start building logical data models, we do practical data modeling. I like to call myself the left shark. Doing this, that's what we do. So let's look at a few data models. Now, I'd rather do this through example in this case. So examples, I feel, as engineers, we all kind of follow, like, oh, that's relevant for me, and I can see the use case. So how about this one? Crazy kids playing video games. So how about top user stories? That's an interesting use case, because it exercises a few different data models. So here's this really overcaffeinated kid playing games, and think about this as a use cases we have as people are playing games and they're finished with the game. It posts a score into an API that goes into a Cassandra database. And at the end of the day, or nightly, we run a roll-up and we show yesterday's top 10 scores for the day. That's something we want to do. So the daily top 10 users, we get to see the scores, and the top users, that'll be a spark job, nightly spark job. So we're going to do a couple of things. We need to ingest the data, and then we need to create a home for this newly created data from Spark. So our user score table. Use cases after each game, score is stored. So this is something that I would consider high-flight data. I had the privilege of working with the Activision Demonware guys for Call of Duty, and that creates a lot of traffic. And when a game like the very popular game like that is launched, you got to be ready for it with your database, and that's why they chose Cassandra. They have a great talk online, by the way, on how they do it. But this is the kind of high-flight data that you're thinking of. Millions of people playing a game, scores are flying all over the place. You need to be ready for that, because what's the least thing you want? Downtime, right? Because that will kill a game. That happened to Battlefield, kill the Battlefield. Call of Duty, no problem. So I want to use a useful data model, something that can store my data and stay online. So what I have is this data model, and I'm doing a little something here. So this is the user scores. I have a user ID, a handle. So, and look what I did. I created a static for that. Bookmark that. I'm going to go into statics in a bit. The game ID, so which game it was. The score, so the timestamp for the score, like when it was actually set, and then the actual score itself. Now, if you look at the primary key, I've got a little something extra going on here. I have two parens around user ID and game ID. What I'm doing is I'm saying that partition key is made up of two parts. I'm going to say the user ID and the game ID are the partition key, which means that it will give it no locality. Now I'm using those because I say that's a unique enough value that it'll never be separated. And I want to create a partition based on those two things. That's super unique for me. I want to create those two things. The rest, the score timestamp, allows for that data model and that clustering columns of the timestamp to let that order really neatly on disk for me. Now the clustering order by, if you recall, means that I want to control the order of the timestamp sorting on disk. I want to be able to reverse that, so I make it descending. Now, if I leave clustering order by off, it will naturally sort, timestamps will naturally sort as ascending. So I'm overriding that default behavior by putting this clustering order by. Now I have this thing where it will collect, I have a data model out collecting, if I play 20 times a day or 200 times a day, it will collect all those scores. And it will be in time order fashion. Cool, so we collected our data. Step one, complete. Our nightly job will be a Spark job. It'll do a group by on a day, and it will do a comparison and store, or it will compare all the scores for everybody who's played a certain game, give me the top 10 of those, and then write that data right back into Cassandra in this table. So you can really feel like this table is a view. We're creating a view of the data. Now, since it's mutable, once the scores are done, it's done. We're not going to rerun that data again. This will help us as we move forward. But top 10 scores are only interesting for 3 days. So I'm doing a little interesting thing here. If you'll notice that, again, I do this clustering order by here, but the default time to live is in seconds. That many seconds, I know it's intuitive, that's 3 days. So any data that goes into this system, into this table, will only live for 3 days anyway. So it just naturally drops off into the default behavior. TTLs are an amazingly cool feature, and is one of the things I really like about it, especially coming from being an Oracle guy. I mean, what happened when you deleted data from Oracle, right? You had to get downtime for that. Especially when you had a lot to delete, or how many had a job that was cleanup. The TTLs allow you to do that without any pain and suffering. TTLs are basically a free delete. If you're not familiar with how they work, and I assume that you're not, what it does is it marks the data with the timestamp. That's how many seconds. When the data gets read, it looks at the timestamp that it was set, does a delta against the TTL. If it's over that time, it doesn't record it, so it doesn't exist. And then it marks it with a tombstone. Tombstone means it's deleted. So it just sits there. It's dead. When the compaction process runs later, and it passes GC grace, that data will then be just not copied from one file to the next. So that's why I say it's less than a free delete, because it's just not going to copy that data. It just quietly disappears, like the homework. So that's a hip chat thing, sorry. That TTL is really good for these type of models because it keeps you from having maintenance. It's a good data maintenance technique. Now, what I did on top of this, which is like bonus points, this is pretty new. This is fresh and just right off the presses. This is date tiered compaction strategy. This is one that I've been begging for a couple of years. Last year I was at Spotify in Sweden, and I met this guy named Bjorn. He was a grad student at the university there. He wrote this. Please, create a Jira. And he did. Date tiered compaction strategies is just knowing that this data, you're using time series data models. The compaction strategy means I want to group all my similar time-stamped data together. Okay? And so, I have a second. It is built for time series. So, think about like all the things that could happen in time series. Is you know that it's going to, the arrow of time is going to go from beginning to end. But these SS tables are a window of time, which gives you a bunch of really cool things. Like all these compactions are grouped by time. So once you group them all together, the times are there together, and they're all TTL the same way. It has the background process. Instead of recompacting that data, if that TTL data is expired, it just simply deletes the file off the disk. It doesn't even process it. It's, oh, that data is expired, delete the file. It could be a 10 gig file, just delete it. That's a very efficient way of maintaining TTL data and keeping your disk nice and clean. So you could drop an entire SS table because it tiered out this way. Pretty cool. So this strategy is purpose-built for time series and TTLs. It's basically creating a tiering of that data on disk and gives you lots of options, but it keeps things very efficient. This is being used in production several places, and it was as good as I hoped it would be, because it really is enabling a lot of really cool stuff, and it keeps the operation overhead really low. So that's why I would recommend that one. So what about the queries? You know, the select queries now are pretty simple. So here's my select for my game ID, process timestamp score, user ID, for my top 10. I can ask for this one process timestamp and get one query. This only takes like a few milliseconds to run. That view is existent. Now, since I have 3 days of data, if I wanted to show like progressions, like yesterday versus today, I'd do it limit 20. It gives you, and that's going to be a pretty quick one. I can just sort it quickly in memory and show the progressions. You know, show that Subsonic was in 3rd place yesterday, and I was in 1st place. So, and Neo lost 1st place. But these are very fast data models. These are views of your data. So this is another one that is somewhat controversial, but I talked to a few people about this today in the lobby. File storage. Now I know this seems like an anti-pattern, but it's not. Brian, can't hardly hear you, man. Pay attention.
I have been, thank you.
You've done this, haven't you? Well,
yes, I've been.
Watch how I do it and see if we'll compare, okay? So, say like you're this guy. He's using 4chan a lot. Doesn't he look like a 4chan guy? He's uploading Kappa videos. Now this is an interesting use case. This actually came from a real production use case. The names and the identities have been changed to protect the innocent. But this was the problem. They needed to have a way to distribute small thumbnails all around the world and file images. And didn't want to rely on things like heavier things like SAN replication that would cost millions of dollars, because they're like, well, these are small images, these are 1K or less. Some of them, like the bigger files, we just want to make sure that they're there. So if we have a 10 meg file, fine. But there's some caveats we're going to look at here. But the idea is we're going to use Cassandra's built-in replication to to our advantage. So if I upload a file here in the US, I want to replicate to my Asia and European data centers for me, and just have it available there for me. So here's the use case. So when the user creates the account, uploads an image, I want that distributable worldwide. And I want to look also, here's the big one, I also want to check to see whenever that image is accessed. So I want to have some, like, hey, you know, if maybe I get, it's a royalty payment. I get, every time this thing is clicked on, I get a royalty payment. Oh, that's cool. That's way better than Flickr. So we're going to start with a query, right? So we need to get all data for an image. We need to, all images over time. We need a specific image over a range and access times for each particular image. So here's our user table. Basic, right? Nothing crazy, but I've added this little thing down here. We're going to talk about this in a minute. This if exists. Now, since it's an advanced data model, this is a big deal. And we're going to talk about this in a minute. This is a lightweight transaction. This is to make sure you do not have a race condition when you create a new user account. So in case, and I will walk through this case, but that if not exists is a big deal when you're creating user accounts. So when you log into Spotify, when you log into Netflix, that user account is running on Cassandra. How do they guarantee that you don't get your account stomped on? So here's the big image table. So the image itself, image table itself, we're going to have image ID, the user, the person who uploaded it, just basic metadata, the name, description, tags. I used a list here, I should have used a set. And we have a list of images. If you look at this as a map, there's text in the UUID. So we have all the different sizes, the original, the thumbnail, the medium size. Think about the sizes that you potentially have for an image. I want to track that. I want to have a UUID per image. This is the critical part of this. So I have one image that I've uploaded, like my cat video, my grumpy cat video, or picture. I uploaded that picture, but maybe I downsample it, I do different things with it. I want to store everything that I did with it in this map. So whenever I go to ask for this image on my user account, it will give me all the different choices. Now here's that access period. So when I have an image that I'm serving up, it's going to the image itself is going to have a UUID. So the image ID is a UUID. So I want to mark when the username and the bucket. That's the username of the username of the bucket. And I'm using a bucket so I can control the size of that partition. So I'm just going to use a bucket of year and month. So this data table will store every event for that image in 1 month. So I can look at months worth of data of access to that image. That's going to be a lot of accessing. You're going to get potentially 2 billion accesses on there before you run out of space. That better be a really complicated image. You know, it's funny, did you notice that, did you see this in the news? Gangnam Style went over 2 billion views and it broke YouTube. Guess what they're using? Anyway. And they had to do some stuff in the back end. Oh, you know, like, there's that whole, nobody needs more than 640K, nobody gets more than 2 billion views on an image or a video. Then some guy's like, there you go. Found him. So this image time series is really interesting because it'll show which ones got like when they were uploaded. It'll be the last image first, but it'll show you can go back and look at this over a month. So now we get into the actual image itself. So this is a list of buckets. Now buckets are what we're going to do is we're going to chunk up. This is our strategy. Is we are going to we're going to try to chunk up. Well, we're going to put images in buckets. Okay, so let's look at the blob. this is easier to show this. So blob itself will be a part of a bucket. So think about like S3. We're building like a baby S3 here. A bucket would be like, would hold a series of blobs. Now, the blob itself would be like, here's an image. Now, we're not saying it's going to be an image of a blob, but what we're going to wind up doing is we're going to take a really large image. Let's say like you have a 200 meg image. I want to chunk that up. Maybe I'm going to chunk it up into 64K blocks. And I want to make it so that I can store this like an inode. So a blob is going to be like the head of this inode, or a file. So the file descriptor. And object ID, how many chunks I'm storing, the size, the total byte size, so I can do checks. I can do checks, the maximum size of the chunks. So these are all checksums, so that whenever I go to read this, I got this. And then finally a checksum, and then some attributes about that. Now the blob chunk is where I'm actually storing the data. So the blob size is up to the client. Now I can change this down to, I can make it 2K or 1K chunk sizes if I wanted to. But the blob chunk is going to store those individually. Now why would I do this? Look at the primary keys. Object ID, chunk ID. And then there's a bunch of data in there. So basically this is a key value store. It's a object ID, chunk ID, and then the data. Why would I do this? And the reason is parallelization. Think about this as a massively parallel operation. If I had a 100 meg file and I broke it into 1 meg chunks, then that means that I could potentially set up 100 parallel streams of 100 different Cassandra servers to read in 1 meg chunks. Now those 1 meg chunks will be read in, checked. If I have an error on one of them, I can reread that chunk again. This is what is useful about this. Think about this as an inode. Inodes in a file system are broken up into pieces. And those pieces are spread out. And then if you lose one, you just reread it again. This is how you can do massive parallel operation on Cassandra and get large files. If you try to stream a 100 meg object out of Cassandra node, your process is going to be sitting there waiting for that one node to read all that data, where you can spread that out all over the place. And what happens if you get to 99 megabytes and something happens on your client? Or something happens in the stream and it gets cut off? You got to start all over again. This is a common enough pattern where I can say this is pretty useful in production. Use with caution, right? This isn't, sometimes storing a file is better to store it in a file system. But in this case, it might not be. We want to use this image access thing, which is more of a distributed topic, and it's reasonable enough where we think we can do this pretty well. And it's going to be fast. And you can wind up caching this if you need to. So the last part of this is the access log itself. And the access log is all about, hey, here's some data. I just served this up. Here you go. So if we keep, this is actually one of my favorite parts of this. The least used data type in Cassandra is the INET. that's a V4 or V6 internet address. And that's a type. It'll validate it for you. So we store the IP address, the time that someone accessed it, and then we can go back and look and see how many times that was accessed. Pretty cool. Now I mentioned that whenever we created the user, that used a lightweight transaction. Let me explain how those work. This was added to Cassandra last year. Formally, it's been baked for over a year now. So it's been used in production. I'll tell you, the places it is being used are pretty hefty. So feel comfortable using it. This is our problem. In a distributed system, if you do a read modify write or read before write, you can run into this problem. Let me explain. I have two separate web processes that I'm going to create accounts on. Process one, I go to create my account. Well, I'm going to go check to see if this username McFadin exists. At T0, T1, I get a return that says, nope, nothing there. At T1, process 2 does the exact same thing. Hey, is there a username McFadin? Comes back, nope, no one there. T1 and process 1 and process 2 now believe there's no one named McFadin in the database. T2 We get an insert on process 1. I insert Patrick McFadin into the database. Good, we got that user account set up. Proceed on your way. Enjoy this website that you can store your random images on. The T2, or process 2, still thinking there's no one there with that name, inserts this guy, Paul McFadin from Oracle, and overwrites my record. That's pretty bad. Right? And that's what happens whenever you have no integrity checks like that. So that's not going to work, right? That's always been a classic edge case with Cassandra, before lightweight transactions. You could not do this. Do not do a read and then a write, because someone will come along and make your day very bad. So let's do this now with the if not exists. Process 1 again looks. It says I'm going to just not even checking. It says I'm going to insert you. Insert if not exists. It returns applied and true. Good to go. There you go. So it checks it. Uses Paxos, which is a consensus algorithm that works across multiple nodes. It's a lock. It says, hold on, I'm writing data into this partition. Writes it. Okay, I'm done now. In that lock period, it checks to see if that data exists. Now here comes Paul. He's trying to create an account too. Right after I did it. I mean, we're talking milliseconds here. Goes to do this. It says, if not exists, create this account. Well, it's going to come back and say, nope, can't do it. That count exists. And I performed an exclusive block, got that data, and rejected. That's exactly what you want. Now, that means that I have a method or a way to get into like doing inserts without creating data loss problems. So that's pretty cool. So there's the fine print. Lightweight transactions are there to solve edge cases, right? Those are those read before write problems that are really hard with systems where consensus algorithms work. They have latency costs because you're going to have to do a quorum and multiple passes to get that data. So just be aware, do some load testing. It is not free, but it is really handy, especially whenever you're just using it, say, for account creation, and that's it. That could be a pretty good use case. I put Zookeeper up here because before we had lightweight transactions, people were using things like Zookeeper to create cages around processes. Whenever you rely on an external system like that to maintain the internal integrity of another system, you'll find all kinds of new edge cases, and I found it. So how else would we use lightweight transactions? Let me show you a little trick here. So this is I had this whole business of form data, form versioning. Whenever you create new forms and you want to create an exclusive block or someone doing some form actions. Well, this is a hard one, right? Because I'm working on this version and someone could stomp. I want to be exclusive in my operation. So each user has a form and they want to do versioning. You can't do that unless you have an exclusive block. How do you guarantee? Well, if you insert something and you say, hey, I've got the lock on this thing, that lock is not exclusive unless you have a way to specify that. So this is not a good thing for a distributed system. Anything that requires a lock like this, like I'm the only one using this and I want to make sure I'm the only one that's got that flag, this could turn into a real big problem. So whenever I'm finished, I want to release the lock, I could have lost the lock along the way. So let's do a little something. This adds in another nuance to LWT, lightweight transactions. So whenever I insert my first version, I say I have a version number, if you notice, of 1, and I say if not exists. And that's part of the primary key. So I would, if there is already a version 1, that form in a version 1, then it's going to stop. Say, no, that exists. Now you need to start working on version 2. So as I'm working on it, I can do an update on that form. You can also, when you do an update with lightweight transactions, you can say if field name equals condition. So you can put in, this is a check and set, CAS operation. So I'm going to look to see if it was logged by me before I update it. If it's not, then it's going to stop. Awesome. So dude, who wants to do it, says, well, if I'm going to make this change on version number 1, if logged by me, dude, and it will reject it. Sorry, dude. It just is not going to allow that to happen. That's a pretty cool use case for this. Because now you have a method where you don't have to do all these round trips with all these like dead zone. Like I'm going to check, I better get that right back before someone overwrites it. Now you have a way to do it singly on the database. So the old way, edge cases and problems. The new way, so much better. You can manage your expectations using lightning transactions. Switching gears a little bit. I'm going to go into some 2.1. 2.1 got released last September. I will be a part of DataStax Enterprise here soon. I want to say a month or two. 2.1 changed a lot of stuff, and it was really, it was one of those definitive milestone releases because it brought some really cool functionality that actually previewed a lot of even cooler technology that's coming in 3.0. One of which is user-defined type. This is got all kinds of potential on it. So this is complex data in one place. You can create a type, like address, with a city, state, a street. That all exists, and you can have collections inside of it. So now you have a type, strongly typed database, right? Schema is typed. And you can do nesting of that data. So how would you use this? So my video example. So I used to have a video table, and then I had a video metadata table. And that means that I had to do 2 selects off my database, do an in-application join, and then push it out to my website. So that's 2 selects. That's 2 trips to the database to get some data. Denormalizing or efficient database, I'd rather just nest that data inside of it. So that video metadata is another table. And that means I have to maintain 2 tables worth of updates as well. Let's fix this. Now I have the type called video metadata. And whenever I go to create my video table, I have this metadata, and I create a set of video metadatas. So I have a set of these. Now I don't have to do any joins. It's all co-located with the same data. That's pretty hip. So if you'll notice, I mean, that looks great, right? Well, there's a keyword in there that you have to notice. Frozen. Shameless plug. And there's some Disney people. Sorry. All rights reserved. All right, so fair use. The technical debt is a big deal, right? And what we did with Frozen, we were trying to stay out of technical debt. And that means that whenever you create a metadata or a user-defined type and you add it to a set, making it frozen means you have to update that. You can't change it. You cannot change the metadata. You cannot change that user-defined type. It is frozen because we're not allowing collection of maps and maps, that sort of thing, like dynamic data sets. That will be there in 3.0. So what we're really doing is pre-optimizing. You can do that operation without making it frozen. This was taken from Ruby, by the way. So you can take, in 3.0, you can create like this metadata, video metadata, and not make it frozen. So it will be mutable data at that point. It's just that we're trying to stay out of technical debt. So it's applicable to user-defined types and the topics. Now, I think the user-defined types that, well, this is a big one. How about some JSON? I get asked this all the time. How do I store JSON in Cassandra? I'll show you. Again, this is the first shot on a 2-shot deal. Let me show you how we're going to do 2.1, and then we can get better after this. So if you look at this JSON right here, let's break it down into some user-defined types. So we have a type called dimensions. So this is like a product catalog. This is pretty real world. We see this a lot. Product catalog running Cassandra. Oh yeah, that's a retail website. Product catalog, but it's a JSON. So the dimensions are a user-defined type, and then we have this categories where this thing could, this kitchen table could be in home furnishings or kitchen furnishings. Well, so we have a user-defined type for a category that has a page, an URL, the dimensions have units. So those are 2 user-defined types. Here's our final table. Note what I did. I took the static portions of that data model, and then I created some dynamic user-defined types based on those other subparts of that JSON. And I can start nesting those if I need to as well. But, so I have my dimensions and categories as a frozen with just one single thing. Notice there's only one of those. And if I need to have more than one category, I'll just create a map. So now, when I go to store this with an insert, I can take that JSON that I got, store it directly into my database. It's all strongly typed. Strongly typed JSON. That's new. Sorry, that was kind of a shameless jab. But I like types. I cannot lie. So this type JSON that's getting stored in your database now is doable because you can nest the parts inside of it, and it's also queryable. So now whenever I want to retrieve fields, back up. Now when I want to retrieve fields, I can say select dimensions.height, because that's a feature of UDT. And I can get exact height. Now I can drill into that JSON. I can go down into a nested part of that JSON. Or I can grab the entire categories field and I get the JSON back out. Well, it's a map in this case. What's coming in 3.0 is formal CQL types for JSON. That's all it says. Yeah, that's good. It means we'll be able to do JSON in Cassandra. It's actually in trunk right now if you want to try that. So these will be CQL commands. So insert JSON, select JSON. That's all going to be there. And so the world wants to use JSON. Cassandra is going to be ready for it. And that'll be cool. But it will be strongly typed schema. It will not be random. You can't throw data in Cassandra and have to deal with it. It wants your schema. So with that, I have 5 more minutes. How about some questions?